Heteronuclear diatomics. Go team. So what we want to do is we want to look at how do you find the wave function for heteronuclear diatomic, more importantly, the energy. So let's start with everybody's favorite. Don't, that's not everybody's favorite. That shit'll kill you. Anyway, but it's beautifully electronegative because we know that the electrons are going to be mostly on the fluorine. Okay, so we have big psi equals coefficient of the hydrogen, wave function of the hydrogen, plus coefficient of the fluorine, wave function of the fluorine. So this is going to be the linear combination of the atomic orbitals. And we're assuming now that there's a so this relates back to the idea that you're going to have linear combinations of orbitals that share the same symmetry. And so the s orbital and the s orbital of the f are going to bond together, and then the s orbital and the p orbital of the f are going to bond together. But in terms of energy differences, we've got H1s, F2p. So if this is full ionization, so here you've got an energy scale. So here you've got 13.6 electron volts. That's a number that's just handy to have in your back pocket. 13.6 electron volts is the ionization energy of the hydrogen atom. And it's just good to know what that is. Okay, here, actually I'm gonna put a minus sign because this is down from that value. But this, the F2p, minus 17.4 electron volts, which would be a 7. Such that if you were to create the atomic orbitals, or sorry, the molecular orbitals, you would have something that looks like this. And I believe your book has this figure 10.39 or 9D.3. So 10.39 or 9D.3. Okay, but what's really cool about this is we have psi is equal to 0.24 psi H1s plus 0.97 psi F, and this is the 2p. Does that make sense? Think about what that represents. So pause me to do that. So here we have 24%. So this is the proportion of psi H1s contributing to the molecular orbital. 97% is the proportion. So here you've got the proportion of psi H1s, but 97% of psi F is contributing to the total wave function of the molecular orbital bonding together. So 97% of the fluorine character of the wave function is contributing to the molecular orbital. And that's what these coefficients represent. Cool? So the kicker here was, again, H psi equals E psi. So these wave functions are chosen such that they optimize the lowest possible energy that you'll get from the linear combination of the atomic orbitals. Those wave functions have coefficients in front of them. And those coefficients are going to reduce to that value that optimizes the energy, i.e. gives you the lowest energy. You could have a wave function that gives you one here, or here, or here, or here. Those are nowhere near as stable as the lowest energy option, which is the one that optimizes the coefficients, 24% and 97% of each of the wave functions of the respective atomic orbitals. Cool. Ta-da. Pause for a second. Hello. So I have now made this easier in terms of erasing. Okay, so I've made this now generic. You've got some heteronuclear diatomic A and B bonded together, and you've got a total wave function equal to the linear combination with the coefficients in front. Okay, so psi A squared, this is the absolute value of Ca, the coefficient of A squared, because remember, we're dealing with probability distributions, you want to take the square of the wave function. That is equal to the proportion of the wave function of A that yields the molecular orbital, that contributes to the overall molecular orbital. So one of the things that's cool is if you compare the coefficients, you can have, so if Ca squared equals Cb squared, this is where we define a pure nonpolar covalent bond. Go team. So a pure nonpolar covalent bond. And a pure covalent is kind of the language that's used where you have an equal sharing. If you have a true equal sharing, it's a pure covalent. If you don't have an equal sharing, i.e. from your hydrogen fluoride example from before, if say one of the coefficients squared is much, much greater than, or just greater than the coefficient, now you have a polar covalent. So this is the definition of polar covalent. And what's really cool is if you have, say your coefficient from A is 0, and you only have the coefficient for B, such that this term right here is 0 and you've only got that coefficient, but you still have a molecule. Guess what this is called? Dun, da, da, da. Ionic. Isn't that awesome? Go team. Cool. All right, so next what we're going to do is we're going to determine how do we find these coefficients. And that's a little tricky in terms of the mathematics, but I'm here to help you out. So I'm going to erase this and be back. Go team. So the goal is to find the coefficients Ca and Cb of a diatomic that optimize the energy E. So there we know total molecular orbital is equal to the linear combination of the atomic orbitals with the coefficients out in front. H psi equals E psi. This is always where we start when we're talking about optimizing energies. So here is the simplified, sorry, not simplified. Here's a Schrodinger equation. If we want to find the expectation value, so this is what the electron, or what the energies could be. This is what they are after measurement. Okay, remember back to the descriptions between finding all the possible energy values. There'd be an n here, and you have all the different ones that are likely, and then this would be the actual energy that you would measure. Okay, so this all comes from the variation principle. The way that we do this comes from the variation principle. And the variation principle says that any arbitrary wave function that you select, any one here, is always going to give you a value of the energy that is greater than the true energy. So if this is the true energy, and here's a scale of energy versus whatever coordinate, you will always have one that's above this line. And that might seem a little strange, but when you're dealing with molecular orbitals, you're dealing with approximations. So there's going to be some approximation that you make that'll give you a wave function that may represent the system. Then there's going to be a tweak that you can make to that wave function. There's going to be an orbital approximation that you're making. There's going to be another approximation that you're making. Each of those approximations are going to add up and move you away from the actual true energy. And they will always move you this way. So the approximations keep you from the true energy. The takeaway of this, and so if I just read this, the variation principle. Oh, actually I can write it. Go team. Any arbitrary wave function of psi used to find the energy will always give a higher energy than the true value. So what this means, it really doesn't mean that you're never going to get to the true value. You could pick a wave function that gets you to the true value. What it really tells you, and what it should be rewritten as, you will never find a wave function that gives you an energy less than the true energy. What would that mean if it did? Think about that for a second. God, that's a fantastic exam question. Wink. So if you have, say, let's go back to, I don't know, fluorine, hydrogen. So you pick arbitrary wave functions to represent fluorine and hydrogen, and this is the true energy. Like if you truly could have a wave function that could represent the two here, and you found a wave function that represented both systems, and it was a molecular orbital that gave you an energy down here, if this is the true one, you're saying that you're better than nature, that you're able to find a wave function that can represent the system's energy in an energy that is lower or more stable than is the most stable that nature chooses. That's really what the variation principle is saying. So you'd always find one in your approximations that is above that, or equal to or above. Go team. Okay, so now I'm going to set up a series of equations with the goal of how do you find the coefficients, Ca and Cb, and how do they relate them back to the energy. Go team.